Okay. Find the area of the region that lies inside those curves. So that's the first question I want to discuss. Okay. I need the area. Okay. So curve, so when I equals 3, consider another one is I equals 3 cosine theta, right? So the regions inside those curves. Now, first of all, you have to draw the graph, sketch the graph, right? It's a periodic function, right? And sine theta could be negative, could be positive. So when theta is 0, I is 0, right? So this is the, but when theta increases, I increases. So this looks like that, okay? Right? You can quickly draw the graph. And then when theta is greater than pi over 2, passes pi over 2, and then r decreases, so all the way to 0. Okay. So that is one piece. Okay. Now when theta is negative, when theta passes pi, and r will be also increased, but it's negative, right? So actually draw the picture on the other side. Okay. So this is a graph. Now, if you are not sure what the graph looks like, and you can try to look at this equation, I multiply both sides by r, then here's x squared plus y squared equals 3y. So this is a circle, actually. Okay, this is a circle. This is another way to help you to understand the graph. You get a circle, and then x squared plus y squared minus 3y, right, equals 0. Then x squared plus y minus 3 over 2 squared equals 3 over 2 squared. Okay. So, so this is a circle with a radius with a center here 1.5, right? 3.3 over 2. So another one, if we got this idea, then how about r equals 3 cosine theta? That would be r squared equals 3r cosine theta. So x squared plus y squared equals 3x. And similarly, you will get x minus 3 over 2 squared plus y squared equals 3 over 2 squared. Okay. So this is the circle around here. Okay. So we are talking about the area of that region. Okay. We're talking about the area of that region. Okay. That's right. This is move it to the next slide. They're going to have enough time to prepare for it. No. All right, so this is the circle, right? Then you find, you're trying to find the area of this, right? Okay, so you have to find out now, some problems even can use elemental methods to find, but this one, you have to find out to the intersection point, right? Where the theta in and the theta, and this is and let me draw the pictures like the that one. Okay. So the idea is by the symmetry. The idea is very simple. you draw the line from here, right? And you just need to find the area of that piece, right? You multiply by 2, because the other one, this portion, this is those two are identical, right? Right. So all I have to do is just find out the intersection point at which point this triangle they are intersect, right? So 3 cosine theta, 3 sine theta equals 3 cosine theta. Okay. So clearly, theta, when theta equals pi over 4, those sides are both equal. Okay. So this is the pi over 4 for the first piece. I equals 3 sine theta. Okay. For that one, and here when theta equals pi over 4. Okay. So this is the intersection. So then by the area will be double of the area of this shared region, right? So that is going to be the integral from 0 to pi over 4 and the 1 half, okay, in the r squared. And the dc, right? So that is the integral pi over 4. I is going to be sine theta over 3. That's 3. Okay. Then it's going to be 9. And the integral of pi over 4 sine theta is going to be 1 minus cosine 2 theta divided by 2 to theta, right? Then you find the antiderivative of 1, which is theta, antiderivative sine cosine 2 theta will be sine theta divided by 2, right? And differentiate that with 1 minus. Okay, so it's evaluated to end point. It's 9 over 2. Here's a pi over 4, right? And the minus sine pi over 4 multiplied by 2 pi over 2. And then you plug 0, yeah, all 0, so that's it. And then 9 over 2 pi over 4 minus 1 half. So that is the answer. Okay, let's go back to the problem again. Okay. Yeah, you don't need to either even this is a region in the two between two in two curves, right? Okay, even this is a region between two curves, but you cannot find the area is the difference. Okay, and you find the intersection point, and you find out that these two regions are symmetric. You can divide by 2. And one side as this part, you can simply be squared by this equation, and theta runs from 0 to pi over 4. So you just need to find the area of that region, and you can solve the problem. Okay. Okay. Well, using elementary mathematics, you probably can also solve this problem. But that is a problem for the students in the middle school, which maybe you heard about this thing called math count. Okay, this is a very good problem. How to do that? Well, this is a two. This would be the two section. It's not easy. Let me. I'm trying to solve the problem. Okay, this is a two section. So you find the area of that, and then you find the area of this part, add them together. But you have to add them together will be the area of this region. But then you have to find the subtract, the overlap part. Okay, So yeah, the idea is that first of all you calculate the area of each sector, okay, and add them together. Okay, add them together. Then this part, the common area is double counted, right? so if you add these two areas together, then minus the area of the union of these two parts, you get the area of the intersection. Okay, that's how you can solve the problem using elemental mathematics, because this angle, you have to figure out that angle. You have to figure out that angle. Okay. Right. If you are able to figure out the angle, then you can solve the problem. Okay. Because area will be theta r squared, and depend half theta, times r squared. Okay. I'm not going to work on this. This is not, we don't need to check this. Well, problem, let's see, maybe I have a, this is a difficult problem, honestly. Yeah. Okay. Problem number 5 is a similar. All you have to figure out is the angle between when to when. Okay, so that's for that section. Okay, and similarly, yeah. So this is this is the problem r squared equal sine 2 theta. Now you can express like this one, sum up, right? So how do you get the other piece? The other piece is because I is negative, right? So for every angle, so let's see, when the sine 2 theta is going to be positive, right? Otherwise, it's not defined. So when theta is between 0 and pi over 2, right? Then sine 2 theta is positive. So that's why you see when theta increases from 0 to all the way to pi over 2, you get this whole loop, right? And how do you get to the negative part? The negative part is because r could be negative, so that's why you draw the other side also. So that's what you get. So theta from 0 to pi over 2, and this equation gives you two loops. So all you have to do is just find the area to integral from 0 to pi over 2, and 1/2 r squared is theta. And you already know r squared is half of, it's sine 2 theta. Then you find the antiderivative. The antiderivative is 1/2 times, okay, right? Negative and cosine 2 theta, right? And you differentiate the negative sign. So that's why I have to put a negative sign. Yeah. Okay. Then you evaluate cosine 2 pi over 2 is cosine pi minus cosine 0. So this is the -1 minus 1 is -2. So the answer is 1. Okay. So that's it. All right. Now, chapter 11 is very important chapter, but it's also very abstract. The reason some students will feel difficult is because you have to prove things, except for first section, and you have to find you have to find a way to give a complete argument to prove why this is convergent or why that is divergent. You cannot just memorize memorize some things, so it's without understanding, okay? So you need to practice on this. I hope you pay attention, okay? Pay more attention, and on average, the test score will be lower a little bit than the previous chapters on this chapter, okay? A sequence, okay, this is about sequence, the first. A sequence usually denoted by a notation A sub m, okay? A sequence, right, usually is denoted by the sum, and the n is not necessarily to be from one, from any letter to infinity, okay? Now, if this is our notation for sequence. Actually, if you want to write down all the numbers, it looks like the beginning was a n plus 1, capital N plus 2, and so on. So you have infinite many numbers, as this is a sequence. For example, here's the example. If an equals, right, n over n plus 1, that I'll give you a formula, okay? N is greater than, and I also put a notation n start from 3, 4. It's not necessarily from 1. Then the sequence n from 3 to infinity, okay, and can be written in the form like that. When n equals 3, and the 3 over 4. When n equals 4, it's 4 over 5. When n equals 5, it's a 5 over 6. Okay. Now let's take a look at this sequence. Okay, and you note that this sequence, right, can be written in the form you divide by n, numerator denominator, so you get 1 over 1 plus 1 over n. Okay, so as you can see that, okay, this one approaches 1 over 1 plus 0, which is 1, as n approaches infinity. So we may say that the limit of this sequence is 1. Okay? Yeah, we have infinite many terms. But the numbers in this sequence approaches 1. Yeah, we needed to know there's a behavior of this sequence near infinity. Okay, we cannot write down all the terms, right? But at least we want to tell something, right? In the future, okay, what happens, okay? And if it satisfies certain, if this sequence of numbers, if the numbers in the sequence satisfy some rules, right? Some conditions, then you can tell how does it look like in the future, okay? When n goes to infinity. Okay? So some sequence are given by a relationship among the numbers in the sequence. Okay? For example, n is greater than or equal to 3. Now, what does that mean? Okay, and we also have an additional term. A1 is A, A2 is B. Okay, so let's see how does this sequence look like. Okay, I hope we can find a kind of formula. Let's see. So A3 equals A plus B, right? A4 equals A2 plus, that's the first one, yeah. A3 plus A2. Okay, so it's A plus B. Let's go this way. So it's going to be A3 plus A2. So A3 is already a B plus A2, so it's A plus 2B. Okay, then A5 is A4 plus A3, right? Then you will get 2A plus 3B. Okay, I'm not sure you can figure out the pattern. A6 is A5, okay, plus A4. So that will be 3A plus 5B. Now you will see that 2, 3, 2, 3, 5 right now, okay? And here's 3 is I think it's 3, right? So A7 is 3A plus 5B and plus A5, 2A plus 3B. So it will be 5A and A to B. Okay, it's not easy to figure out the general formula. Okay, but it's clear that the coefficients of A and the coefficients of B is increasing. It's getting larger and larger, right? So if you write down the coefficients, okay, if you write the coefficients of A, and you will see that the first one is 1, second one is 2, that's A5, and then the 3, then 5. Actually, the next one will be 8, okay? The next one will be 8 because it's just a sum of those two numbers. And the coefficient in front of B, okay, and the first one, the first one is 1, the second one is 2, yeah. 1, 2, 3. What is where I start? Oh, actually, this is yeah. I begin with A3. Okay, I begin with A3, and that is 1, 2, 3, and 5. Okay, 1, 1. Here's 1, 2, 3, 5, 8. A3, A4, A5, A6, A7. So those are the coefficients. And the only difference between those two is B is the one after the A, right? So not the one before that. See, okay, those are the correspondence. Okay, so if you know A, then you can get the B, the corresponding term. Okay, and it's almost impossible to get a general formula, right? So that's the pattern. So you can figure out the coefficient, and clearly, you know, if yeah, those coefficients goes to infinity, right? And very quickly. All right. Now some sequence, okay? Some sequence they're given by a function, okay? So n is greater than or equal to n, where n where f is a function. Then you can say that, okay, so if, okay, so this is a fact. If we know the limit of x approaches infinity of this function has a limit to L, then we must have yeah, this is an important fact. Then we must have n equal, okay, of course, right? Because when x approaching infinity, x takes all the possible real values approaching infinity. Of course, in particular, when x takes n, and you should have the same limit. Okay. If you're using this fact, then you may able to answer the question. For example, if an equals sine equals n sine 1 over n, right? Now what is the limit, right? Find the limit n approaches infinity. And first of all, you can express n as a function of n, okay, f of n, right? Where f of x equals x of sine 1 of x. Okay? Then you're trying to find the limit as x approaching infinity. Now, only when you change the variable to the x's, then you can use the Lupitus rule. Okay, have you heard about Lupitus rule? That's what we studied, right? Okay, so this is a 0 over 0 type, so you can apply the Lupitus rule. Okay, then so this is going to be cosine 1 of x. When you differentiate the 1 of x, you get a negative 1 of x squared. When you differentiate the denominator, you also get the negative 1 of x squared. Okay? So this is cancelled out, and that is going to be limited as x approaches infinity, cosine 1 of x, which is cosine 0, which is 1. Okay? So then you can say that then the limit of an, right, is going to be 1. Okay? You have to for a correct solution, you have to change the variable, because you cannot apply the Lupitus rule to the variable n. N is not a continuous variable, right? Although you can think of it that way. Okay. Another important theorem we can use is called the squeeze theorem, sometimes called sandwich theorem. Okay. So if the sequence, okay, n is between two sequences, but those two sequences are very, very nice. They both approaches the same number L, okay, as n approaches infinity. Then the one in the middle also approaches that number. Okay, so that's obvious, right? We can, in particular, okay, if absolute n less than equal to Bn, and Bn approaches 0, okay, then the limit of n also 0. The reason is the absolute over n approaches is bounded by Bn. Bn approaches 0, so absolute n approaches 0, so n approaches 0. Now you can also you can also apply the above general result, right? So n is between those two, but this approaches 0, the other approaches negative 0, right? The negative 0 is 0, right? So n approaches 0 too. Okay. Okay, that's a picture. All right, so let's take a look at the following problem. Okay, sine n over n. Wow. Now, this is different from the above problems. Right, here's a sine n over n. Now, how can I find the limit? Okay, you say I'm going to change it to a function, but still you have the same problem. The sine x over x, right? You cannot apply the Lupitus rule to solve the problem. So this is the wrong way to do, right? If f of x equals sine x over x, because this is not a 0 over 0 type, infinity over infinity type. So the limit of this is not going to be the limit sine x, cosine x, and 1, okay? And the limit of cosine x as x approaches infinity is that you don't know, does not exist. Okay. So this is a part, yeah. So this is a wrong idea, okay? So you cannot change the function, cannot use any other method to solve the problem. You have to use a squeeze them, make observation first. Sine is a numerator. It does not change too much, but you don't know the values, okay? It's harder to figure out the values. But what we know is absolute of sine over n is less than equal to the numerator is less than equal to 1. So the denominator is n, right? So that one approaches 0, right? So therefore, we can conclude that sine n over n equals 0, okay? We conclude that. Right. And the next problem is natural log of n over n. Now that's a different. Natural log of n over n. This one, it's not easy to estimate natural log of n. Okay, natural log of n also goes to infinity. It's different from the above problem. Okay, so maybe we have to change to natural log of n over n is going to sine over n, and this f of x equals natural log of x over x. Okay. So first, we find the limit of f of x. But this is an infinity over infinity type, so you can apply the Lupitus rule. And this is 1 over x, that's 1. And clearly the limit is 0, okay, by Lupitus rule. Therefore, this is the limit is 0. Okay. Okay. Now, sometimes sometimes let me state the theorem again. Sometimes we have a function x approaches L. This has a limit, okay? F is continuous function, so you have this, right? And if we know the limit of a Bn equals L, then the limit of f of a Bn, now this is another sequence, right? Is going to be f of L, okay? So as long as f is continuous at L, then if Bn approaches L, then f of Bn approaches f of L. Right, that's obvious, right? Okay, and if using that, we can and solve the problem the following way. A is going to be, okay, A is going to be cosine n pi over n plus 1. Okay. So here f is cosine. So as long as this one approaches some number, then n will be approach of a cosine for that number. Okay. So the limit of n is going to be cosine of the limit of n pi over n plus 1, which is just equal to pi, because n over n plus 1, the limit is 1. So it's cosine equal pi, it's negative 1. Right. Yeah. Yeah, what I was trying to say that if f is, here's a, yeah, if, yeah, that's how the, let me move to this side a little bit, okay? So, so in other words, if f is continuous at L, then the limit of f of Bn equals f and the limit of Bn. Okay, so that's you can switch it. So here, yeah. So L is the limit of Bn. Okay. If Bn has a limit, which is L, and f is continuous at L, then you just switch. You just plug the limit of Bn for x into f, then you get the limit of f of Bn. Okay, so just like what we did. Okay, our next problem is n is natural log of n plus 1 minus natural log of n. Find the limit of an. Find the limit of n. Okay. Well, this is the difference of two terms. Each of them goes to infinity. Okay. Okay. What I'm going to do is I have to modify this function in. Okay. Then this sequence is like a f of another sequence, n plus 1 over n. So the limit an is going to be natural log of the limit n plus 1 over n. As long as this limit is as long as the limit of n plus 1 over n exists, and actually this is going to be 1, then the answer is here. Okay. Or without using this formula, you just solve the problem directly, natural log of n plus 1 over n. You can divide the numerator by n and denominate by n. Then you will see that this limit will be 1 plus 0 over 1, which is natural log of 1, which is 0. You can argue. Yeah, you can express the answer in this form. Therefore, you can write down again the conclusion. That's a 0. Okay. Okay, I'm going to try to find this limit. One plus 1 of n to the power n. Okay. But this should be equal to the limit as x approaches infinity, 1 plus 1 over x to the power x, right? If you know, yeah, because this sequence, right, is going to be f of x and f of n, where f of x is going to be 1 plus x, 1 over x to the power x, right? All right, so the question is, how do you find the limit? You have to modify this function. I hope you still remember. It's going to be e to the natural log of this function. Okay. Then the x is moved down to the front of natural log. So all I have to do is just find the limit of this part. Okay. What is the limit of this? Okay. You can even change the variable. Okay. If you let 1 of x to be theta, like if you can keep it 1 of x. Okay. But if you exchange, yeah, let me try. Yeah, if you change the variable, that is better. Otherwise, it's just a little bit complicated. That's okay. We don't need it to change. Okay. So this limit, it can be 1 plus 1 of x. Okay. So when x approaches infinity, the numerator approaches natural log of 1, which is 0. So this is a 0 of 0 type. Okay, this is a 0 of 0 type. Okay. So you can use a Lupitus rule. You will get this 1 plus 1 over x. You see, the derivative is more complicated, and then negative 1 over x squared. And the denominator is also less. So these two cancel out. And then the limit is clearly going to be 1 over 1 plus 0, which is 1. All right, so we go back to above limit. So clearly, there's going to be the limit e to the x of natural log of 1 plus 1 over x, which is e. Okay. So in other words, we conclude that so in order to estimate the number of e, you just choose a very sufficient larger n. Okay. Yeah, where this is from, what we have to deal with. This number. Okay, it comes out naturally. You have no choice. Okay, if you invest the money, initial deposit, right? Investment. You put a certain amount of money initial deposit into the bank. I is going to be the annual interest rate. Annual interest rate. Okay. Then in T years, okay, so the interest will compound monthly, okay? It's a monthly, compound monthly, okay? Then in T years, the balance will be 1 over, right? Compound monthly. So I is So the interest rate, it's we use a decimal point as numbers, and you have to divide by this. So monthly, so every month, that is the interest rate, right? You have to divide by like a, so right now the interest rate is very low. It's maybe even 1%, but the monthly will be 1% divided by 12, okay, right? Okay, monthly. Then T is how many months, right? It's the N time, okay? So if monthly N is 12, but if you compound N times a year, okay? So then so N times per year. Okay, then this is a formula, okay? So that is a balance in T. Then you have to find the limit. Suppose it's compounded continuously. That means N is going to be sufficiently large. Then you take the limit, okay? So how do you find the limit? And you end up with a period to the RT. Okay, so actually the limit is going to be the limit when n approaches infinity. Okay, is going to be e to the t. Okay. So okay, so this is how do we calculate the variance in T is. I don't know what happened. My computer. All right, so let's take a look at another problem. And the next problem will be an equals the nth root of n. In order to find the limit, find the limit of n. Okay? In order to find the limit, you just need to find the limit of the following function, because n equals f of n. Now, what is f of x? F of x is x to the 1 of x, right? We just needed to find the limit as x approaches infinity. Right. But this function is going to be, can be written in the form of this. So which is going to be e to the 1 over x natural log of x. Okay, but natural of x over x, this limit is going to be 0 as x approaching infinity. Why this limit is 0? You can apply the Lupitus Rule here. Okay, and this is 1 over x 1, so that's what the limit is 0. Okay, because it's the infinity over infinity type. So that's just 1. So therefore you can conclude that the limit of nth root of n is going to be 1. Okay. How about this problem? N equals -1 and to the power n over n. Okay. The easiest way to solve this problem will be you take the absolute value. absolute value is going to just 1 over n. You get rid of the negative sign. And clearly this approaches 0, right? As n approaches infinity, right? So absolute value approaches 0, of course, then you conclude that the limit of n is going to be 0. Okay. Another way you can think about is negative 1 over n is less than or equal to 1 over n, greater than or equal to negative 1 over n. It's between that, right? So both sides approaches 0. Of course, the one in the middle approaches by the squeeze theorem. By the squeeze theorem. All right. So in general, right, we should know the following fact. Natural log of n approaches infinity, but it's slower than any power. Okay, alpha is positive. And then this is not the absolute value, it just grows slowly. And that grows slowly than any exponential function. Here a is greater than 1. That may be slower than n factorial. Okay, then maybe this is much slower than n to the nth power. So that's a sequence. So it depends on which one is on the top when you compare. So my conclusion is the limit, okay, so the limit of an over n factorial, that should be equal to 0 because n grows much smaller than n factorial. Okay. Now, how do you see that? How do you see that? How do you see that? Why this is, I just said give you this fact, but you have to give a proof. So let's take a look at n over n factorial. If you write down, you have lots of a here. Okay, and here's 1, 2, 3, all the way to n minus 2, n minus 1, and n. Right? But I still don't see why this goes to 0, right? So the idea is that a is a finite number. So what you do is you cut somewhere here and you cut somewhere here. Okay. I'm going to choose a number. Here's k. I'm going to is this a? This is a case term. Okay. So I want to make sure choose a k so that k is going to be k is greater than or equal to a. Fix k. That's okay, right? This is a finite number. It's not, does not depend on n. Okay. Then what happens? All of them here are going to be less than 1. So this less than or equal to a over 1, a over 2. I have to keep this k minus 1, okay? And here's less than 1 because the denominator is larger than the numerator. The numerator is always equal 1. And then I keep the last one, okay? Because I want to use that to make sure this approaches 0. So this is a constant, right? It's independent of n. This approaches 0, right? That's enough. That is why this is approaches 0 as n approaches infinity. That's not easy to prove, but that's a trick, okay? And that may be much easier to understand the following: an over n factorial. Just let a to be 1, okay? So you have a 2, let a to be 2, yeah. 2, 2, 2, 2, 2, right? It's 1, 2, 3. N minus 1, n. And then you look at this, all of them will be less than 1, so you don't worry about it. 2 over 2, 2 over 3, 2 over n. So this less than equal 2 times 2 over n, it's a 4 over n. So that's approaches here, right? It's easy to see. But here's our in above example, a could be maybe 100. So that's why you have to keep those terms. Okay. All right. Another fact is, we're going to find the limit and r to the power n. Okay. Here's r is any real number. Okay. And this, I'm going to give you the answer here. This will be 0 if absolute I is less than 1, less than 1. And it is 1 if, obviously, if I is 1. But the limit does not exist. Does not exist if if I is negative 1 or absolute I is greater than 1. Okay. Yeah. Greater than 1, could be positive infinity, but we just say divergent. Okay. So this is this is this just considered as a fact. Or how do you prove that? Well, if a number is less than 1, between negative and positive 1, when you multiply it, every time you get in smaller and smaller number. Okay. If you look at A, okay. So if I is less than 1 greater, right? Then r to the x, okay, y equals r to the x. How does the graph look like? The graph looks like that. Okay. When x equals 0, that's 1. Okay. And then when the x goes to infinity, the graph approaches the x-axis. Okay, so we will use this fact to solve the following problems. Okay, assume that where's the limit? Okay, assume that I is between negative and positive 1, and find the limit as n approaches infinity, 1 plus r squared all the way to n. Wow, I have many terms. But this is a sequence, right? So this is my an. This is a geometric sequence by finite sequence. So an, you can combine them. into one term. It's one over 1 minus r to the n plus 1. Okay, so if you know this identity, then the problem is very simple. Because I is between negative and positive 1, so the limit is 1 over 1 minus r. Okay, so that's why the answer is right. All right, so here I'm going to talk about another theorem. The theorem says that every bounded monotonic sequence is convergent. Okay, so that means here's a sequence. Okay, so this is increasing sequence. So suppose the sequence n is increasing, n is bounded by some number. Why it has a limit? Of course, it has a limit, right? This is A1, that's A2, A3 there, and here's a main. Okay, so the distance between two numbers is getting smaller and smaller, and you cannot pass the number capital N. So there's an upper limit, right? Okay, so some way, maybe not M, some way it's here, accumulate. Okay, so the limit exists. Okay. So I give let's take a look at the following example. Okay, an is going to be square root of 2 plus the square root of 2 plus square root of 2. Keep it going. Okay, so n radicals. Okay, does it have a limit? Yeah, find the limit of n. Okay. First of all, you see that two important factors you have to verify. N is increasing, y is increasing. You just take a look at A1. A1 is a 2. A2 you add a little bit more. Of course, it's greater than A1, right? Right. And A3 is going to be what? A3 you can assuming A3 is 2 plus 2 plus square root 2. Okay. Right. So this part is already gives the A2, right? So it's definitely greater than, you let the last one to be 0. And then this is going to be A2. So it's increasing, okay? So you get rid of the last one, then you get, right? So this is a very important term here. But at the same time, n is always less than 2 for all n. Okay, why? Well, A1 is less than, right? A1 is clearly square root 2 is less than 2, no problem. A2 is a square root 2, right? Plus square root 2, but this square root 2 is less than 2. So square root 4 is 2, right? So it's keep it going like that, okay? And A3 is 2 plus square root 2 plus square root 2. So I'm going to change the square root 2 by 2. Right? Then square root 2 plus 2 is going to be is going to be 2. Then it's 2. So once you replace the last radical by 2, then you immediately get rid of all the radicals. So in general, n 2 plus right? So I replace this one by 2. So once I replace it by 2, all the radicals be gone, right? So here's 2 plus 2 becomes 2, then the other radical is gone, then move up a little bit. So they're all equal to 2, okay? So we conclude, therefore, the limit of n equals L exists because all n has an upper bound of 2, so should be less than or equal to 2. All right. So how do I find the limit? Maybe it's 2, maybe not. All right, I'm going to take a look at it again. N equals 2, okay, over. Right? So you have n radicals here. But how about this part? There's n minus 1 radicals. So this is going to be 2 plus n to n minus, right? You agree, right? Right? Then you can find the limit. Okay, let n goes to infinity. So you get n approaches L. N minus 1 also approaches L. Okay, then I can solve for L. So L squared equals 2 plus L. So I'm going to get, so L minus 2, L plus 1 equals L. L cannot be negative, so L must be equal to 2. So now it's clear that the limit of n equals 2. And similarly, you can solve a problem. Yeah, let's take a look at another problem. Okay, an equals 1 plus 1 over 1 plus. Okay. So you have infinite many, not infinite, but here still have finite many, right? Okay. Yeah. So this is a 1 over. Let's put it this way. Okay. Okay, so here I have to have a n. Let me check. Okay, so I have to have a n lines. Okay, this is the n here. 1, 2, 3, 4. Yeah, this is just only 4 lines here, right? So n lines. Okay. So a1 equals 1 over 1 plus 1, only 1 line. A2 equals 1 over 1 plus. Okay, so now you can understand that. A3 is going to be 1 over 1 plus. Okay, just keep it going like this. Okay. Now this sequence is also, this sequence is increasing and it has an upper bound. It has an upper bound. Okay, so upper bound is going to be, I'm pretty sure it's going to be less than 1/2. Okay. Okay. Yeah, why it's less than 1/2? We can. I don't have much time left. Okay. So yeah, you just the same idea. Just look at this and look at this, and you will see it's less than 1/2. Okay. And then, so it has a limit. Okay, it exists and less than or equal to 1/2. I'm not sure this time L can 1/2, but you will see that. You will see that in order to find the limit, you have to right? Okay, so what they do is this part is going to be 1 over n minus 1, okay? So once you get this, then you take the limit, okay? Then you get, let n goes to infinity, you get a limit. Then you get L, 1 plus L equals 1. Now this time L is not going to. So where's my file? Oh, God. Okay, so yeah, so it's L over 1 plus L. So L squared plus L equals 1. So L squared plus L minus 1 equals 0. Then you use a quadratic formula. B squared minus 4AC. Yeah, so it's going to be minus 1 plus minus square 5 over 2. But our L is positive, so it's going to be negative 1 plus square 5 over 2. That's a pretty strange number. Okay, it's not going to be 1/2. Okay, and this is still smaller than 1/2. Okay, that's a limit. Okay, and why it's smaller than 1/2? Well, it's yeah, you can show that, right? Oh, that's greater than 1/2. Let me double check. 1 plus, no, it's not smaller than 1. So L squared plus 1 minus L, so it's B minus C. Yeah, it's greater than 1. Square 5. Okay, this is actually called the golden number. Yes. Well, let me stop here and see you next Monday.